Hello, my name is Eric Moskal. I'm technical expert with Cascade. We're here out on this former industrial site debuting our automated injection system. We have 54 injection locations with a crew of 4 guys and 2 drill rigs. And this new automated system is currently pumping on 10 locations at the same time. So the automated injection system allows us to set pressure thresholds and flow rates that we want to achieve on each leg of the injection manifold, as opposed to a standard manual manifold where the individual operator is adjusting things manually with their hands. The computer system in there will allow us to set, for instance, a 1 GPM flow rate threshold not to exceed 15 psi. And the system will allow liquid to flow through the automated valves under those conditions. If the pressure threshold is met, the system will reduce the valve as much as possible to keep the pressure below it. Same thing if the flow rate exceeds past 1 GPM, it will reduce. If we're not achieving 1 GPM flow rate, the valve will open and allow liquid to flow through until we reach our pressure threshold, and it kind of balances itself out between there. I'd like to talk today about some of the field data that we collected from the first application of the Pathfinder automated injection system. And first, I'd like to show you is the raw data that the unit spits out. Um, so what we start with here is a text file, and it records the data every second from the moment you turn the machine on to the moment you turn the machine off each day. Creates a new file for each calendar day that it's utilized. And in each of these files here on the top here, we have flow trend. So this is the flow meter data for legs 1 through 10 and the master flow meter on the pumps recirc. And then down here, we have the pressure trend data. Same thing, same date stamp every second. And we have our 10 pressure transducer legs. So we take this data and then we import it into a template, such as this, where the PSI data gets imported here, GPM data imported here, and then for each leg, we generate a pressure and flow over time. For any given day, there's 1,440 odd minutes in a day. So this is just the template in case we ran for 24 hours, which we normally wouldn't do, but these axes automatically adjust for data that's inputted. And then once we actually input our data, we get this. So this is demonstrating pressure in orange and flow in blue over time for a particular leg. This is leg 6. And that leg 6 corresponded for this data to transect number 1, injection point number 2 on this date. And what we see here is a increase in flow. We started our injection and pressure came up. The unit was set for a pressure maximum of 15 psi and a target flow rate of 1 GPM. The valve opened, flow came up, and it spiked up. So the unit started to restrict flow rate a little bit, and then it opened it back up again. We exceeded 1 GPM, which is our target, so it restricted again, and then it allowed the valve to kind of open slowly, and we established a fairly steady state for the rest of the injection with this little bit of a down spike here. This reflects where we switched over to a new batch tank. Corresponding to that flow rate trend, we have our pressure graph, which shows fairly stable pressure. As our flow rate increased here, our pressure kind of dropped off to a steady state. No sharp spikes, indicating that we did not fracture the formation, which was key for this location. And this really highlights the flexibility of the unit, because this is fairly on the low end of what we would apply in the field. We're pretty shallow here. We're under 10 feet below grade, and our target was 1 GPM flow rate, low flow, due to the shallow nature of the injections to try to avoid daylighting. So this is very low on this unit's capability. We have the capability of going to up to 10 GPM per leg, all 10 legs running at the same time, for a total of 100 GPM going into the ground. For this project, we utilized large-scale tanks for staging water and deoxygenating the water. Water was then transferred over into smaller batch tanks where we could add the liquid and the dry amendments and blend them together in 250-gallon IBC totes. So we were mixing 250 gallons at a time, and when you're running, up to 10 legs, even at 1 GPM each, we got to switch over every so often. So this drop off here, it happened to come at a point where the data system was recording, because it takes 1 point every minute of data. So we just happened to spot on when we were switching over tanks right here. It caught it, but otherwise this would be a nice steady state graph. The unit displays all of this data for us numerically in real time. We're watching pressures and flows on the display of the unit in real time, and we can even have, they're a little cruder and a little more difficult to see because they're on a small screen, but we can actually see graphs just like this in the field in real time. So we're observing all of these things happening in real time in the field. But as far as the data output goes, in order to not have thousands of data points for each graph and running 10 legs at a time, the system spits out data once every minute. So every 60 seconds, whatever the instantaneous reading is on either the flow meter or the pressure transducer, that's what the data logger grabs and dumps into the output file, which is perfectly fine under long-term injection under steady state and steady flow, steady pressure states. That's perfectly acceptable data resolution. And then from here, we take this data and then we print it out into our PDF deliverable, which then we can mark up with some pertinent information. This particular graph represents interval 1 of IP2 in transect 1 on this date, and it gives the depth of injection, 9 to 11 feet, and any sort of pertinent deviation to the data from what we would expect to see is defined here. This was our batch switch where we switched over the tanks, and this would be what is generated on a per point per day basis. So if, for instance, if we were injecting on IP2 for longer, this represents only about an hour and a half of pumping time at the end of the day. If we were looking at an entire day's worth of pumping time, we would be able to break this up into intervals. So we could show that this section of the graph represents this interval, this section of the graph represents a different interval, so on and so forth. Well, from a decision-making perspective, it looks like we can take this data, especially if we had this unit available for a pilot test application where we're defining what the lithology can withstand as far as injection pressures and flows and stay below that fracture threshold. It can help us better design a overall duration on the project and be able to really hone in on a specified time and cost. It might also give us an idea of if certain intervals are going to be problematic, certain locations on the site are problematic, as far as being able to achieve the target flow rate, or maybe there's some minute changes in lithology that aren't reflected when looking across monitoring wells, but when we're doing a grid of points, we might find some zones that are less receptive, or that we have to maybe approach in a different manner.
So this is Elliot Cooper, Vice President of Technology, and one thing I wanted to add here is that on any project trying to go to full scale, it's important to be able to define your pressure and flow limitations. And typically, we would do that at the completion of a high-resolution site design optimization activity and get that data while we're completing that project. We have a smaller unit that we use specifically for hydraulics testing that works under the same principles as the Pathfinder in terms of pressure and flow control and data monitoring. But once we get those parameters, then we move into full scale. And then with the Pathfinder, we use those pressures and flows to actually set our limitations before we start the project. Obviously, there's variability at a site, and so we'll have to adjust those as necessary, but going into a project, we'll have a good idea of what those maximum pressures and flows are going to be, and those will be our set points starting the project. We spent a lot of time trying to figure out an appropriate name for this technology, which is an automated injection technology. And we really, after much debate, came up with the name Pathfinder, because in fact, what we're doing here is using this technology to help us deliver amendments into the flow paths or flux where contaminants are residing. And so that's where we came up with that name. And really, to accomplish that, it's very important to understand pressure and flow in these flow paths to get that distribution in contact.
Another bit of data that the unit collects that we don't have displayed here yet is the level sensors that we put into adjacent monitoring wells. We can monitor up to 3 wells at a time for groundwater elevation during injections to make sure we're not overmounding a particular injection area. And that data can be displayed in a very similar manner to this, where you can see a baseline value, and then you can start to see creep upward, and actually the groundwater table subsiding while the crew broke for lunch in the middle of the day, and then once they came back and started pumping again, you could see the groundwater come up again to the high water mark for the day, and then settle back down once they had finished injections. So we're still working that data into a display model.
While the Pathfinder is unique technology and actually a major enhancement in injection technology that has been stagnant over the last 20 years, it's really part of a three-pronged approach to expediting groundwater remediation. And the three pieces that are important to the overall solution and results are: first, the high resolution design optimization, and that's where we find where the contaminants are and what type of lithology they're residing in. Very important information. Secondly, is we have to have a chemistry that's going to provide high residence time and persistence. And that's where the cascade chemistries come into play, like our Fluxorb IS colloidal carbon or our cleaner IZVI colloidal ZVI compound. So those two steps are critical. And then finally, the ability to deliver those chemistries into contact with the contaminants is where the Pathfinder sort of completes the cycle that's required for a quick pathway to closure, results, performance, and another reason why we've named that system Pathfinder.